Hi, this is Junaid, back with another video. Today we're going to discuss the technical basics of machine learning in healthcare. In this presentation, I will introduce to you what are the different modalities of machine learning and how they're going to be applied in different aspects of care. Outline of the series, if you remember that we actually discussed in the first lecture, which is the prelude, is why physicians need to pay attention to this. They were initially sidelined when EHR implementation was done without any consent for physicians or their usability or user experience. It was just made as a billing engine. And now we're going to see a second revolution that's going to come through. And if physicians are not have their own say in it, unfortunately, it is going to be a repetition of the same problems that we see with EHR implementation. In the brief overview, I actually discussed how the interdisciplinary other technologies like genomics, robotics, AI in different fields, communication technologies, etc., are going to change, which is going to show what is the real game-changing potential of machine learning and artificial intelligence. As a matter of fact, the Stanford AI Lab ex-director, Mr. New, compared it to electricity, and even the metaphor for internet doesn't do justice. In this lecture, the technical basics, I'm going to discuss what are the different forms of and flavors of machine learning and how are they being applied to healthcare. Again, we're going to have then separate series for neurovascular disorders, etc., and then go into acute ischemic stroke. These are all slides that are completed. It's on my website, and then eventually these recordings are going to come through. So what is artificial intelligence, machine learning, and deep learning? These are the three definitions that every physician should know to realize where we are and where we're going to go. Artificial is a technology that mimics human decision-making, and it encompasses multiple forms of machine learning into a one cohesive whole. It is a few years down the line, maybe even 100 years down the line, depending on what your expectation of artificially intelligent bot would be. Machine learning is a subset of artificial intelligence, which specifically wants to control or devise a method where any piece of software learns by itself. It could be statistical learning, machine learning based, or it could be non. At the end of the day, if that particular piece of software can improve upon itself, then it is considered machine learning. Deep learning is a form of machine learning that is the whole craze. People talk about artificial neural networks, convolutional neural networks, etc. What it empowers is that you do not particularly have to train a lot on deep learning, and you will get the results, which has a big downside, which is explainability of the AI or machine learning. But at the end of the day, this is considered the breakthrough in machine learning. And this was in AlphaGo, and we're going to give you some more examples. Machine learning is a science that teaches and focuses on how computers to program themselves or improve on the data set through training by themselves. No particular output, explicit programming required. So what is the real difference between statistics and machine learning? This is the key factor that we have to understand. As far as deduction, which is statistics, is considered, we formalize a theory, then perform a hypothesis, do the observation, and then confirmation. Classic model of studies in medicine. What machine learning differs is that when you have induction technique, you formalize a theory and hypothesis, but it's all onto your head. What you see is observations, relations, correlations. Then you find out the pattern through them. And when you find out the pattern through them, then you create a hypothesis, and then you create a theory. It is more exploratory in nature, and therefore does not require explicit programming. You just throw the data on an algorithm and it will tell you where to look, and then you test it again. One more way to look at it is statistics is basically a subfield of mathematics, while machine learning is a computer programming. Statistics focuses on explicit programming, while machine learning learns from the data. The purpose of statistics is to infer what the data is trying to say. In machine learning, the focus is more on prediction rather than inference. The practical implication for statistics is test the hypothesis. In machine learning, make the hypothesis. The data that statistics use is multivariate, but what machine learning can throw in another layer is not just multivariate, but multidimensional. Results of statistics is knowledge, in my opinion. That's just a colloquial way of saying it. For machine learning, you can create wisdom out of the data. Let's see an example. So CHAS-VAS2 score is widely used, at least by stroke physicians and cardiologists. And this is a classic logistic regression model. We had X amount of patients. We ran the logistic regression model. We weighted what the particular diagnosis have an impact, and we predict stroke secondary to AFib. Again, this is very linear method of thinking and linear method of prediction. It doesn't improve on itself with new data. It doesn't gather more knowledge. It doesn't adjust the weight of the different variables. If the same thing was in machine learning, we could just say that, over time, if a patient comes in with that age of 45, hypertension was truly the big problem. And how would you adjust automatic weighting of other variables? Similarly, in South Asian people, CHF, because of long-standing hypertension, could be an issue. But in South Asian people, if you have one stroke before, that matters a lot. But otherwise, it may not matter a lot. So machine learning has the ability to have a multidimensionality to be applied on the data, and it can adjust itself on the situation on the fly. So this is truly the difference between statistics, able to learn and able to adjust. And this is truly the birth of medicine 4.0, which we use now called precision medicine, where the number needed to treat is actually 1. Statistics, mostly through public health databases, confer to applying 100 patients onto one patient, and there's an art to apply these studies. What machine learning will take care of is that it will apply the study through the prism of individuality, and will it be able to create more new biomarkers, individualized predictions, individualized therapeutics, and monitoring. And these will change medicine and healthcare at a fundamental level. The resource allocation for monitoring will change because you will be able to predict who needs more monitoring, who needs less monitoring. With the advent of genomics, drug discovery, as a matter of fact, from molecule to medicine, the complete drug discovery model has been changed with machine learning. Individualized prediction will actually see what is your age, race, sex, and then, or locality, whatever other different variables that we can collect massively can go through and again keep improving on it as more and more data is fed into it. So what is neural networks? I can actually go into a big 2-hour lecture on that just by simply that. But what it is important is that this particular video really is fantastic. So it will go through what are the layers, hidden layers, convolutional networks, etc., and how it actually parse out the different areas of that particular topic that you're looking at, and then apply one layer of network after another, and this will actually produce the results that you're expecting. Those layers can be adjusted, and explicit programming can be applied, which introduces a bias. So scholastic approach versus holistic approach are two different approaches in data sciences. And this video is fantastic. So if you want to get into more detail, please review this video. Classically, machine learning has been divided into two big camps. One is supervised learning and one is unsupervised learning. Let's start with supervised learning. Supervised learning is that you actually give a small data set or a large data set, let's say of cats, and then you personally classify them And then when you have classified them, you shove it into the machine learning algorithm with another data set, and this will start producing results, and you can test what is the accuracy of that. Unsupervised learning works differently. You just throw in cats and dogs and let it cluster itself without really pre-training on it. By pre-training means labeled data, and on the supervised machine learning, that's labeled data, and unsupervised, no labeling of the data is required. It requires more computational power, but it decreases significant amount of bias that can be present. This also produces a decreased cost of labeling, which is quite labor intensive in some situations. Now we go into different other forms of learning that is more important. The biggest one is reinforcement learning. Reinforcement learning is that while you throw in the whole machine learning into an environment, the reward base and the policies of that environment can be defined, but it doesn't automatically generate the results. It just continues to look at all the possibilities of single move results. And with that sequential decision making, you're able to produce the results. It is most likely reward-based reinforcement learning can be applied on supervised machine learning, but is more so with unsupervised learning. The second biggest deal in healthcare is natural language processing. The whole idea behind is teaching the computer to read, write, and listen. Google Voice, Amazon Alexa, all these technologies are related to somehow natural language processing. From a healthcare perspective, we have seen implications in reading radiology reports, highlighting critical findings, Alexa in hospital, and we'll go over that. And the last one is machine vision. Machine vision is the technology where computers are learning how to look at images and draw inferences from it. So if you see the whole landscape of machine learning, the idea is that it mimics human learning, but there are so many variations that we go through, and these make the changes in its application. The other big thing you need to understand is active versus passive learning. So if there's a data and then you have labeled data, then that's passive learning model, and then you get an output. But in the form of active learning, you have semi-labeled data that goes into the active learning model, and then the computer starts looking at it, and let's say it's dogs, and then suddenly comes to a picture of wolf, and it doesn't know what to do about that. The computer is not confident enough, so it's going to generate a query, and then at that point in time, you label the product, the wolf, and then it can continue doing that, and suddenly it's going to continue to improve on itself. And this is truly one of the magnificent time-saving, resource utilization-based active learning process. The example is that we have been training this machine learning for a long time. Recaptcha is a Google company now. What it did was that initially, if you remember, handwriting analysis was done, and then you would put it in, and they would have two words. One of them was the labeled word, and the other one was the unlabeled. If you corrected this one, that means that you have correctly identified this one. And then it was given to millions of people, and then suddenly we have a trained model of machine learning by using this technology, freely trained by millions of people. This now is being applied to self-driving cars. And as you can see on all these images, you're basically asked to identify traffic lights, cars, etc. And by definition, you and me are training an algorithm for free. If you want to learn more about it, go to this Verge video, and it's going to talk to you about Amazon Mechanical Trunk and other services that are commercialized now to actually produce more and more data. And we're going to see some examples in medicine as well. Clearly, as you can see, one of the things that Google is doing is taking generative adversarial networks and applying machine learning into it and creating itself some scenarios while driving. So as a matter of fact, Waymo now has 10 billion virtual miles that has driven, and it A, can create scenarios, and B, can automatically find pathways, and gives it to, in the active learning process, throws it to the programmer and say, is this label correct or not? And this way, the computer data accuracy increases, and of course, overall safety comes first. So that's how Waymo has been doing this. However, the semi-supervised learning model, if applied in healthcare, is, to be honest with you, completely scary. You only take about 10% of the data by reducing the cost of labeling, and then augment that by computer playing by itself. So what happens is that in this situation, if you can see the image, that when it was 10% label data, the top one accuracy was 68%. But if you had fully labeled data, the accuracy increases to 79%. This is kind of scary. Again, organizations will look at cost saving, and if applied to healthcare, this could be a big problem because the accuracy decreases mainly because of saving cost. When we were talking about deep reinforcement learning, so reinforcement learning was environment, which is, as I suggested, and then an agent. And then if you do the right thing, it's going to reward you. And if you're going to do the wrong thing, it's going to unreward you. And this is tied to the state as well. So if you have an environment, what you are able to define are the policies behind the environment. This is an excellent video. And if you see that this car is trying to park, and this is just a complete bad start, and this is attempt number 1. And if you go, we are now at 2502 attempt, and then eventually we are looking at I think 50,000, 31,000, 3,100,000. So as you can see, the more and more the machine learns by itself, and what you have done is define an environment and define the reward, and you're done. And let the machine do itself, and then it will automatically learn how to park better. OpenAI.com is mind-blowing. If you want to further explore this, the first one is to see the Rubik cube by a robotic hand. They didn't write a policy for every single move, and that would be impossible. You will write millions and millions of lines of code. What they did was they produced a mechanism through artificial intelligence and machine learning that it, again, when it tries to move the Rubik cube and tries to solve it, I mean, not just move it, solve it, it actually goes through and learns again by itself. So fantastic to see this. The second big thing is multi-agent interaction. So one, in the reinforcement learning, I told you that there was an environment and one car, but what if you had 2 players or 5 players? It is genuinely mind-blowing to see these two. So please look into them if you have time. So now let's come to computer vision. I'm going to start with that first because that is clearly the application that most people are familiar with because of Facebook, image recognition, etc. So if you look at deep learning application in image analysis, this is the YouTube/Facebook model. You have the original image, then you change that image into different levels, and then each particular image has a feature selection process. So you can look at different features at all, and then it goes into the convolutional network, and then you can know that it is a cat. This is the classic model of machine learning. Similarly, it is applied onto the brain MRI. As you can see, there's an input image, a convolutional layer, a pooling layer, fully connected layers, and then it can define if it is a tumor or not. So computer vision practically works as the same way as other kinds of image analysis through machine learning works. And it has gone through a significant amount of update from the past even 5 years. image analysis, when you're looking at it, is divided into three big things: classification, detection, and segmentation. I'm not going to talk about super resolution right now. The classification, as you can see from 2012 to 2016, has improved in accuracy, and it has actually improved in resource allocation in terms of computational power needed. Then you have all these other algorithms for detection, and then finally segmentation. So let's see what that means. So if you're looking at classification, you can see one is normal and one is possibly malignant. And you can see that the first and the foremost is to actually detection. And it detects an abnormality. And then once it has detected the abnormality, it marks it down and segments it out. Very good example from breast cancer. From a brain MRI perspective, what we want to know is what is the volumetric. So once you have the segmentation down, then you can actually apply that segmentation into very different ways. This is an example of looking at ventricle size and what is the amount of atrophy that is done. If you follow these serially, I'm going to have a talk on Alzheimer's, and you're going to see how this is applied. Another way of segmentation is to look at the various volumes of the brainstem. And as you can see that in this multiple sclerosis, you are able to classify what the segmentation has been. So now let's move to natural language processing. This is the key technology of machine learning that's going to transform, again, the way we receive information, the way the summarization of anything, critical findings, communicated, and of course, chatbots. So let's take it one by one. Natural language processing is if you look at it, to be honest with you, I don't understand the technology that good. But at the end of the day, what it is able to do is all the language can be synthesized, semantically analyzed, and that analytics can produce more robust way of communication and presentation. For example, if you look at the acute ischemic stroke subtype classification, in this particular example, they applied this and then was able to show, extract from the EHR, what is the TOAST classification. If it was done at a massive scale, you can completely transform the way the research of stroke epidemiology works. And in clinical practice, this could be a way to audit. For example, one physician writes TOAST classification and calls it lacunar, the other one different, and then the radiologist reads it completely differently as a lagoon. At the end of the day, it produces an internal audit system as well. If you look at it, this is another study which they looked for 75 critical findings were seen in 591 reports. What the NLP was able to pick up are those critical findings. And once those critical findings are picked up, the benefit of that would be the latency of communication will significantly go down, because at the end of the day, these findings need to be communicated. And on top of that, if it is actually if this particular findings can be communicated over a text-based system like Tiger Connect or whatever, then you will have a complete different transformation and decrease in the workload of physicians in just communication. So very important findings from natural NLP applications in machine learning in healthcare. The biggest thing that's going to change is also what we term intelligent scribe. This is Microsoft project, and as you can see, while the physician is having an encounter with the patient, it is able to scribe automatically. And once that scribe is done, it will be able to show it as a whole note, and then you can edit that note. This clinical documentation of using neurolinguistic programming is going to change the way we practice and communicate medicine via clinical notes. The next big thing from NLP is virtual assistants, Nurse Alexa. As you can see, people have been using this technology in the rooms already to better communicate, be able to order food. I mean, have you seen the nurses? Unfortunately, I feel sorry for them that they have to sit and be on hold for up to 20 minutes just to order dinner for the patients, which is not acceptable, and this is not the work they're supposed to do. The last NLP application is chatbots. I have to admit, I haven't looked into it that much in detail, but the chatbots are going to be especially important in patient to physician communication. And these menial tasks of scheduling, etc., will become thing of the past, and patients will be able to reasonably communicate non-urgent stuff. And if they have urgency to it, then it could be escalated in a manner that actually works for both patients and physicians. These are different machine learning algorithms. The Bayesian networks are based on the Bayesian statistics model, and it has a higher prediction value, and that is very important and used in precision medicine, especially in oncology and genomics. Decision trees are looking at what are the regression of models and at what points we're going to have decisions and how we're going to move through it, etc. Clustering, as I've told you, is important for making sure. One example that comes to mind is they just released a software that will automatically find the sequences of MRI. Deep learning, CNNs, deep belief networks are fantastic, and they will potentially change the way we do anything, including medicine, as far as decisions are concerned. Unfortunate part is that it is still hard to explain, and that's one of the major limitations of this system. Then we look at regression models, rules, regulations, neural networks. This is just supposed to be an introduction to machine learning algorithm. This is not the be-all list. There are many different forms of machine learning algorithms more than this. So this is an excellent article by Beam, Big Data and Machine Learning in Healthcare. And as you can see, when we are actually looking at this data sample size on the bottom, and then relative human to machine decision-making effort, you see the more and more the data sample size increases, the machine learning gets better and better for producing more wisdom out of the data. For physicians, we're looking at, a trial, case-controlled studies, or double-blinded studies, and you can see they are very good at applying that. But as you go furthermore, you can see that let's point to number 23. So number 23 is mortality rate estimates from US Census. Huge amount of data, but again, it technically can be interpreted by the humans. But if you go in and let's say Google search number 12, you can see that there's a massive amount of data, and then you need both machine and computers. And if you come to number 6, Google AlphaGo, the amount of data isn't that much, but interestingly enough, the computer wins every day. And then lastly, generative adversarial networks, which is something that I did not talk about in this technical study, is because what it basically is that two competing algorithms compete with each other and then keep producing results. This is the most efficient way of producing deep reinforcement learning. So as you can see, the more the data comes, it can be applied in various ways. And therefore, we need to understand that sometimes machine learning do need to be applied, but that doesn't mean that we have to apply it everywhere. Plain old statistics worked best in certain situations as well. So we have to also find if the machine learning needs to be applied as well. I hope you enjoyed this whole talk. The next one will be Principles of Machine Learning in Healthcare. Again, please visit, provide me feedback, subscribe to my YouTube channel, put a thumbs up, and then definitely share. It is very important for me to actually have this into the system, because again, the whole idea behind is you as a physician needs to be empowered, and otherwise we will have another billing engine on our hands. Thanks for listening.